Using a syringe to investigate air pressure, one might think, would break the connection with the human activity of sucking. But the common sense anthropomorphic terms persist.
Right. Can I have a look at your drawing then, Paul? You got any water in your drawing?
Yes.
The water in the syringe is where?
Just up to there.
Just up to there, yes. Now, how does the water get into the syringe?
Well, there's this little hole here.
Goes about the hole there?
Yeah, and the rubber part makes it come up.
Right, so the rubber part makes it go up through that hole, does it?
Yeah,
so
and just sucks it up.
So how does it suck it up?
Well, I think it's got some things on the bottom of the
yes.
rubber part. The rubber part makes it come up.
What sort of things, do you know?
Wait, let's go get it. Got nothing on it.
Yeah, it's got nothing on it, so how does that make the water go up?
It's probably that makes it, pulls it up.
That pulls it up?
Paul is only momentarily surprised by his failure to find any things on the bottom of the plunger. But science lessons could lead him to see it as an interesting problem.
In the scientific concepts, there is a search for coherence, which is much less clear in children's thinking. Children will be much happier with inconsistencies in their thinking than scientists will be.
I think there's a very big difference between scientific thinking and common sense. Common sense is about natural expectations. It's what you learn from everyday life, as it were. Scientific thinking is a rather self-conscious approach to the world. And it just so happens that the world isn't built on a common sense basis. It's nobody's fault. Again and again, you come across ideas that are just totally against your expectation. It's very irritating. And when you get to really complicated things like quantum mechanics or cosmology like the Big Bang, I mean, common sense breaks down completely.
Scientific ideas have to be taught. Formal scientific ideas have to be taught. They don't develop spontaneously. Now, the reason for that is that the ideas of science include concepts and theories which are, in a sense, imaginative constructs developed by the community of scientists. They are not entities that you discover by looking at the world. Ideas such as genes and chromosomes, energy, magnetic fields, these are not things that you see in the world around you. These are constructs that have been developed by the scientific community. Now, as a result of this, children can't be expected through their own experiences to invent those ideas for themselves.
Children do gradually acquire more scientific concepts as they get older. In a century where scientific and technological explanations abound, this is unsurprising. But while the effects of teaching are easy to detect in the use of specialized terms, for example, a lot of other ideas continue to coexist. These girls are 9 years old and are investigating flotation. The boys that follow are 12.
I find it quite light. What do you think? Try it out, Nina.
It might plastic. It doesn't usually sink. It's wax. Yeah, it's wax.
Wax. Wax doesn't usually sink. And how about the marble?
Yeah, that would, because it's glass.
You're pretty sure of that one, aren't you?
Yeah.
You too? Okay. What do you think is heavier, this or this needle? Hold them up. Hold them up. Try it out.
That's heavier.
That's heavier. But you said that is going to float and that one is going to sink.
I think metal's a bit heavy.
Oh, I think metal's a bit heavier. When we interview children, very young ones tend to concentrate on the external aspects of objects and the appearances. Children at about 7 or 8 start concentrating on other aspects of the objects that are less obvious, like the weight and what they are made of. And a little bit later, they start thinking that objects are made with more air or with less air inside them. And that is actually a precursor of the idea of density.
Now, tell me something. Why are these floating? Why does plastic float and wood float? Why?
Well, the air can keep it afloat.
The air can keep it afloat. Where is the air that keeps it afloat?
All around it.
Around it. But why is it that the air keeps these afloat and doesn't keep these?
Can't because of its shape, because that one's smaller.
It can't be because of the shape, you said. So why could it be? What do you think?
Could be because of the shape, because that's long and roundish, and that's long and round.
Long and roundish.
But this one's round, and that one's round and it sinks. Yeah, but it's not long.
And now the 12-year-olds. They have a rather original theory about why a needle sinks, but they too are basically looking for air trapped in the objects.
We think because it's got a hole in here, the water will get through.
Right.
Since it's heavier on this side, it will weigh itself down.
Okay.
It'll just sink
Then
down
it would
like
just
that.
sink down like
There's
that.
nothing to keep it
There's
up.
nothing to keep it up, really. This is too thin.
There's nothing to keep it up.
No air.
All right, like what? What could keep it up?
In this one, you can trap air underneath.
Okay, so there might be air underneath. So you said that the car would float.
Yeah.
And you decided it would float just because it would trap air
Yeah,
underneath.
trapped air.
The boys test their objects to see if their predictions were correct. They have some difficulty explaining why a rubber band floated rather than sank, but the memory of a technical term helps them out.
Why is that a floater rather than a sinker?
Well, some of it seems to be staying above water because it's kind of a strange shape.
There's some sort of thing over the top of the water, which I can't remember the name of, and I don't think it's heavy enough to break it.
What,
Maybe.
like some film on top of the
Yeah,
water?
well, the
There's
meniscus.
a special name.
Yes.
Meniscus.
The meniscus. It can't break the
I don't
meniscus.
think it's heavy enough to break
Right.
it.
The boys' understanding is still incomplete and may remain so.
Might be some.
I don't think that children are all that different to us. For many issues about the nature of the world, there's a 5-year-old child really describing or thinking or giving us the explanation of how things work. So I don't think children are that peculiar. I think that there's a great deal of our thinking, like that of Aristotle's, which is very similar.
So when adults are questioned about their scientific understanding, they often answer in much the same way as children.
You pick that one up and see what happens. So how would you explain the difference between those two? How would you understand the difference between that metal and this metal? Saying that they're both the same size, but the same shape.
Density.
Right. How would you explain that?
I wouldn't know how to.
Right. Any offers?
No idea. Just that it's heavier than density. Yeah, I've no idea or how to explain it to somebody.
What is learnt at school, like the word density, is often the end of our scientific knowledge. Common sense makes up the rest of what we know. Only now and again, as adults, do we take the opportunity through play, like children, to confront our naive ideas.
Right, that's good. That's good so far. Try our luck that way. Somebody going to catch it if it falls. Well, that's... I reckon that's fair. That's nearly excellent, isn't it?